Okay, so one of the things we need to talk about is why Earth has seasons. So remember kind of the convention in here, or maybe I haven't used this convention yet, but we'll make this chair of the sun, drag out the sun, okay? And we'll make, this is, I'm going to be the Earth-ish, but this is going to be the axis I'm rotating on. So we know that the Earth spins on its axis, okay, and the Earth also orbits the sun. So it's all about counterclockwise. I'll say clockwise, all about counterclockwise. So you think of a clock and it goes like this, right? So I'm spinning like this, and I'm also orbiting the sun like this, right? Well, when the Earth first formed, and when all the planets first formed, the physics of how they formed, it makes sense that actually the axis of rotation is straight up and down. Straight up, okay? It should be like that. But early on, we think when planets were forming and stuff, within our solar system, there was extra stuff, something about the size of Mars basically hit the Earth such that it tilted. The Earth didn't tilt, but it sort of did. Its axis of rotation now is pointed, it's tilted. We talk about a 23.5 degree tilt. So to me, I go back to the kind of straight up and down, and then I go 23.5 degrees. So that's your angle person. That's your 23.5 degrees. Okay. So now, what the Earth does, and remember that's Polaris for the semester. Okay, what the Earth does is it goes this way. So actually, does this make sense? Does it look like the northern hemisphere is tilted away from the sun? Okay, so you think winter time, and actually this is winter. So what I'm going to need you to know, there's two solstices, two extremes. This is winter solstice, two extremes. Okay, so it takes about 3 months to get here. Okay, this is one of our two equinoxes, but do you see where I kept this tilt the same? Okay, 3 more months to get here, and it looks like we're tilted towards the sun, which we are. This is summer. This is our summer solstice. Okay, and then 3 months to get here, this is our second equinox. So it kind of goes in quadrants, kind of. Okay, so this actually would be our, let's see, we're going from summer to winter. This would be our fall equinox, or autumnal equinox. Okay, winter solstice. Okay, so this is about December 21st, 22nd. Okay, 3 months later, this is, help me out, March 21st, 22nd for the spring equinox. Okay, and June 21st, 22nd for the winter, for the summer solstice. And then fall equinox is about September. So if you look on a calendar, those are 3 months apart. So I'm going to kind of talk you through why does this tilt result in seasons like it does. And there's a few reasons, okay, but if anybody asks you why do we have seasons, it's because our axis is tilted. Check this out. Planets that don't have a tilted axis that they rotate on, okay, they just go their lives like this, they orbit the sun like this. Actually, if you're at the equator, you're going to have a constant sort of season, okay, you won't have seasons. It'll have a constant sort of climate. If you're at the poles, very cold, very hot at the equator. So. All right. So the number of daylight hours changes. Okay. So I'll go back to winter here, which we're coming up on, right? Okay. As we're tilted away, okay, like this, the northern hemisphere is tilted away. First off, can you see where the southern hemisphere is tilted towards the sun? So honestly, when we're at our winter solstice, they are in their summer solstice. Okay? Makes sense. So up in winter, around December 21st, 22nd, winter solstice, that's the shortest day of the year for us, which means we have the fewest number of daylight hours. But here's the deal. If you were to go, and we talked about lines of latitude when we were here last, if you were to go to a latitude of 66 1/3 degrees north, that is what's called the Arctic Circle. So up here, that's the Arctic Circle. And as the Earth rotates, the angle is such that it's dark as the Earth rotates. So it's dark 24 hours up here. Okay. 3 months later, we're coming out of winter in our hemisphere, and we're going to go into summer. So this is spring, right? Actually, as the Earth rotates, this is kind of this equinox is the reason they're called equinoxes is because equal equinoxes, they have equal daylight and nighttime. Okay, so that's the kind of cool thing about that. Okay, as we go on around into 3 months later, okay, over here, okay, this is another solstice. Okay, so this is the summer solstice. And again, if you are north of the 66 1/3 degree latitude, as the Earth rotates, you're going to have daylight all day long. Okay, which could be problematic if you're trying to sleep, I think. They must sell a lot of like window darkening things, window darkening shades. Okay, this picture right here is showing you that the sun is not setting at this particular location. All they did was to take, from the same location, where is the sun? And the sun is here, here, midnight it's here, okay, then it just goes back up again. Okay, so that would be midnight-ish. Oof. So that's one reason we have seasons, okay? The other one, it still has to do with the tilt, okay, but has to do with the directness of the sun's rays. Now this, I'm kind of stepping aside, kind of doing an extra little tidbit of information. So if I were to ask you how many hours in a day, you'd say 24 hours in a day, exactly. And so, like, if I am the Earth, what you're telling me is, as I spin on my axis, it takes, I'm counterclockwise, okay, as I go like this, it takes me 24 hours to come back to noon, which is cool. Okay, that's actually what we call a solar day. But there's something else called a sidereal day. Okay, and I'll highlight the way I think of anything sidereal like that, sidereal day, is I think of the word real within sidereal. So I'm going to show you another type of day. Where did it go? Sidereal. I've heard it called sidereal or sidereal. I like the word real in it. And that's how long it takes to really complete one spin. And I'll show you why they're different. This figure, actually, I'm going to kind of redo what this guy's doing right here. Okay. So what he showed you, or what I showed you a minute ago, is you said, this is 24 hours, which is fine. That's great. The deal is that actually we are also moving, orbiting about the sun. The Earth is relocating. So the problem is I don't know if I can do this, is I relocate, and as I spin, okay, 24 hours needs to be here. I need to go a little bit farther than 360. I need to go a little bit farther than 360 degrees, because I'll do it this way. Okay, so this, okay, go here, and I'm going to do one of these. Okay, so I'm not at noon again. Okay, I'm not at the same location relative to the sun. So actually, to complete so I really need to go an extra 4 minutes. So that is our solar day that we're used to, 24 hours. But to complete your 360 degrees, it's like 4 minutes before that. So it's 23, did I say days? It's 23 hours, 23 hours and 56 minutes. 4 minutes short of that. So there's a slight difference between those two. Okay, so the number of daylight hours vary as we orbit the sun, and the angle varies as we orbit the sun. So we've talked a lot in here where you can kind of like use your hand. Let's see, if you spread it out like this, you can get 20 degrees, right, in your local sky with regard to altitude. Okay, so if the sun is straight overhead, that's like a 90-degree altitude. Okay, if it's kind of lower in the sky, it's got a smaller angle. The bigger the angle, and 90 degrees is as big as you can get with the sun. Okay, the bigger the angle, the more direct the sunlight. Okay, and just the more energy it's going to give you. So that's why, like, if we're looking at when the sun's rays are most intense, they're not very intense in the morning. Okay, they're most intense at noon, and then they get less intense. Okay, and they're less intense actually for a couple of reasons. One is, we call it, in meteorology, we call it beam spreading. One is if you have a big angle like that, basically that shaft of light has a really small target it's spread over. If it's kind of got a smaller angle like this would be what, the altitude, like that. It's got a larger region it's spread over. Okay, it just is, it's more diluted. So as far as the sun kind of going across the sky, what's done here is this. Have you ever noticed in the wintertime the sun doesn't get very high? That's what this is. That's the winter. It's funny, even on a day in the winter where there's no clouds, nice and sunny day, the sun has just a different quality, I think. The sun never gets very high. Okay, so it's always got kind of that beam spreading going on. But also, it's got what we call beam depletion going on. And this actually is trying to show you beam depletion. I don't know if you can kind of see here. If it's at kind of a small angle, it has to go through a lot of the Earth's atmosphere here. This is actually why when the sun rises, it kind of looks orange, and when it sets, it kind of looks orange. It's right here. Basically, when it's low on the horizon, it has a small angle, it has a lot of the Earth's atmosphere. In the wintertime, I go back to the wintertime, the sun has a different quality to it, because you just basically kind of have that sort of, some of the wavelengths of light literally are taken out of it by this. Okay, so beam spreading and beam depletion, it's an angle thing. So if we go back to the left drawing over here, this is in the winter and this is in the summer. So in the summertime, you know, you would see the sun rise its highest. In the wintertime, it doesn't make much of an arc, okay? Or much of a thing. So this is where I get to say, remember where I said just a minute ago, this was our winter solstice. The northern hemisphere is tilted away from the sun, okay? And this is our summer solstice. The northern hemisphere is tilted towards the sun. Of course, here, if we're experiencing summer, they're experiencing winter, right? And vice versa over there. If we're in winter, they're in summer. But I hesitate to say it's not because it's tilted. I mean, it's not this physical tilt that gives it the heat in this case, or the tilt away over here that makes it cold. Because that's kind of suggesting it's are you close or are you far from the sun? This is to kind of remind you, we talked about, Kepler talked about, or we didn't, that's coming up. We already talked about perihelion and aphelion, and you guys can't read this, okay, but this says winter, December solstice, and this says summer solstice. Okay, they're about January 3rd, so maybe here-ish or so, January 3rd. Okay, every year we are at our closest point. This distance is at what we call perihelion. Okay, i.e. close. So my point is going to be is if over here, wait, right here, sorry. This is winter. If over here, this is cold for us, right? This is as cold as it gets. But we are literally 3% closer to the sun, okay, in our winter. Okay, and we're 3% farther from the sun in our summer. So it's not a proximity thing. It's the number of daylight hours, the sun's angle, having the effect of being either direct sunlight or indirect. So I'm going to go ahead and let me add one more term over here. There in July 3rd or so, we are actually in what we call aphelion. We are farthest from the sun. Okay? All right. Now this is kind of a standalone topic. So we said, like, during the formation of our solar system, the Earth got bonked, and it's been tilted 23.5 degrees ever since. So what it does over the course of 26,000 years is basically it keeps that tilt, but instead of pointing at Polaris, it's going to point in some other direction, not necessarily even a star. Okay, it's going to stay tilted, but it's going to make kind of like a cone in space, kind of like a top, like that. So this is showing you, actually it's got in 15,000 AD, we're going to be pointed up to in the vicinity of the Star of Vega. I don't know about you, but 15,000 AD, I'm not going to be here. Okay. So, and the thing is, as this is kind of done like a coning motion, it's really subtle, like you can see. It takes 26,000 years to go one full circle like that, one full cone. You know, as the Earth orbits the sun, that actually is going to change when our seasons occur, just ever so slightly. Okay. This phenomenon is called precession, just like the slide says. And since it changes when the solstices and equinoxes occur, sometimes it's called precession of the equinoxes. It's very gradual. Very gradual. All right. The moon. Okay, now we're going to switch gears, and that is going to be the Earth, and I'm going to be the moon. So one of the things you guys already know is that the moon orbits the Earth, right? The moon orbits the Earth, but the moon also spins on its own axis. And I don't think its axis is tilted. I just now thought about that. I don't think it's the axis of the moon is tilted. But it does counterclockwise, okay, just like the Earth orbiting the sun. So the moon spins on its axis counterclockwise, and it orbits the Earth, okay, counterclockwise. And it does all of that in 29 and a half days. Now, I already introduced you to something cool about the moon. The fact that it completes one rotation and one orbit in the same amount of time. That's in sync. We call that synchronous rotation. Okay? And we'll come back to that. So hold that thought. All right. So what we're looking at here in the little center is a little blue dot. That's the Earth. And so the black circle here is showing you the orbit of the moon. And just kind of like there's the sun is off-centered from Earth's orbit, so also the Earth is off-centered from the moon's orbit. So it has two important locations. It has apogee, kind of like aphelion, and perigee, kind of like perihelion. So here, let's see, you see this distance right here? 356,000 kilometers. Okay, that is the closest place. So the moon is here, and we would call that perigee. Perigee? Perigee, final answer. Okay, so that's closest. And over here, as the moon orbits the Earth, farther, we would call that apogee. Must be. Okay. So, there we go. We have, I kind of got ahead of myself. We have two supermoons coming up, back-to-back supermoons. And what a supermoon is a full moon when the moon just happens to be closest to the Earth. So is the moon going to look bigger? A little bit. Okay, supermoons. Then the last thing to talk about kind of leads into phases of the moon. Let's go ahead and make like the sun coming from over here. The sun's over here, okay? I am still the moon, and this is the Earth. So the thing about it is the reason you see the moon, it doesn't light up itself. The reason you see the moon is because the light from the sun shines on the moon, and then it's reflected back to you. So I'm going to go clear over here. I'm the moon, okay? The sun's over there. Can you see where basically all the sun hits me on this side, and that sunlight goes back to you to see on Earth, okay? Does that make sense? This is actually a full moon right here. So that's the only reason you see the moon. So I have a figure coming up here in a minute to kind of walk you through the phases, full moon, new moon, that sort of thing. But as I walk through the phases, I want to kind of introduce a term called the terminator. Okay, so the way the terminator works, by the way, I'm going to make this a quarter moon. I'm going to actually make it first quarter. first quarter moon. And the first quarter moon looks like this, where this is dark. I bet you guys have seen a first quarter moon before. This side is dark and this side is light. So the word terminator, it means this area right here, as I have the hash marks. That is the terminator. And I mention that because if you do any viewing, like, if you go to an observatory where they have a telescope turned on the moon, a lot of times they'll go right along the terminator with their telescope because that's where actually you're going to kind of see some interesting features. The other part's going to kind of look flat sometimes. Okay, so phases of the moon look like this, where this helpful young lady is the Earth. She's the Earth, and she's extending her arm to hold an object, which is the moon. So if we kind of jump to over here, this one right here is a full moon. That's me. I'm a full moon. Okay. Notice that the light is shining on this half of the moon, and this is the half of the moon that I can see at nighttime. Remember, you're on the Earth. You're on her. Okay. Do you see the counterclockwise? My next step would be right here. Okay. I'm the moon. Okay. So now here's the deal. As I face the sun, okay, half of me is lit up. The back half of me is not lit up. If you're on the Earth, do you see that actually you are going to see that this is the disk of the moon? You're going to see this half lit up, okay, and this half is going to be dark. So it will look like this. Okay? That's what I call it the last quarter. It's called the third quarter. Okay? And that's where I am right here. So now let's go on, and I'm going to go right here. Okay, by the way, each of these quarters takes about a week. Okay, so now the sun's over there, okay? So the sun's lighting up the front side of me, okay? But do you see where you can't see any of the lit part? All you see is the non-illuminated part. This actually is where you can't see any of the moon. This actually is a new moon, okay? And then I'm going to go a week later, and I'm going to be right here. So again, the front half of me is lit up. Okay, but if you're on the Earth, all you're going to do is kind of see a circle with this part lit up. Okay, that's actually what we call a first quarter moon. Okay, then a week later, I'm back here, where you see the whole disk, a full moon. Okay, so those are the major stages. The full moon to third quarter to new moon to first quarter. Those are the main stages. Any questions about that? Okay. Well, we see some stages in between. And this actually is to kind of tell you how do you get the stages in between. So 29.5 days kind of rounds to 28-ish. Okay, so if you round down to 28 days, that's why you can kind of divide the whole moon orbiting the Earth into sections of 7, because they're a week, right? So you basically could have a week here, a week there, a week there, and a week there, kind of. So here we go. This first bit, okay, where it goes from a new moon to a first quarter to a full moon. So that would be right here, right? New moon, okay, to a first quarter to a full moon. That's actually called waxing. And the term waxing just means we're seeing more of it. Kind of, you wax, I don't know, you're adding something. Okay? We're seeing more of the moon. So we call those waxing. The other thing is that we use the term crescent for anything that's less than a quarter. So specifically, let's see, how would that look? Specifically, when I'm about here, okay, I'm past new, on my way to quarter, okay, I'm waxing, okay, but it's just the fact that I'm between new and quarter means I'm a crescent. Okay, then I'm here at first quarter. Then, when we get after first quarter, on my way to full, Actually, we call that a gibbous. So if you're seeing more than a half of the moon, but not the full moon, then that's a gibbous. So that would be a waxing gibbous because it's getting larger on its way. One of the things I tell students that sometimes it's hard to kind of orient kind of how the terminator is, but if you find the terminator, it's nice, clear up and down like this, whatever is on the right is going to continue to the left. So if it's lit up here, the lit up is going to continue from right to left. It's kind of how it should work. So that's a full. All right. Then after here, okay, going from full moon to new moon, what does that look like? Well, actually, we call that a waning process. So waning kind of makes sense because it's kind of you're seeing less of the moon. So here's a full moon right here, okay, and this is third quarter, okay, so you're seeing less of it, and then this is new moon. Not only that, waning, but you're going to go from a full moon to a waning gibbous because it's somewhere between full circle and a half circle. We call it quarter, so it's gibbous. So that's a waning gibbous. Then, of course, this is third quarter or last quarter. And then over here, before I've gotten to the new moon phase, I'm smaller than a quarter, but not moon. And you can see a sliver, that's called crescent. It almost looks like a crescent roll, right? Okay, that's crescent, and it's a waning crescent. So that's kind of how those all go. All right, so back to synchronous rotation, the 29.5 Earth days it takes for moon to rotate on its axis and also to orbit the Earth, okay? The fact that it has synchronous rotation has this effect, okay? The thing, have you ever heard of the far side of the moon? There actually is a back side of the moon that we never see. And the only reason it goes that way, that the same face of the moon is always pointed to Earth, is because of synchronous rotation. So what you see here is no rotation here. Okay, so here's what that looks like. So I'm the moon, I'm going to orbit the Earth, I'm not going to rotate. So I'm just going to go like this. Okay, so I'm not going to rotate. That's kind of what that figure's showing you. Over here, this is synchronous rotation. Over here, on the right. So here's the deal. This is what the moon really does. It twists on its axis as it orbits the Earth. So I'm twisting. I'm going to complete one twist, one rotation by the time I get back to new moon again. I know it's a subtle thing, but if I weren't spinning just subtly as I orbit, okay, that would be this left one, and this is this right one, okay? So because of that, actually, we only see one side of the moon. We see the pretty side. The back side of the moon, what we call the far side of the moon, actually is popped, kind of cratered. And that makes you wonder if kind of the moon ran interference for for material that otherwise would have cratered Earth. So it's kind of taken a beating over the years. All right, so lunar and solar eclipses. Okay, so lunar eclipse coming up September 27th, did I say? I think so. We'll have to look on the internet to get the details. But a lunar eclipse is when the moon goes dark. So here we go. I bet you buy this. So remember now, I am the moon, this is the Earth, and the sun's over there against that wall. So does this make sense that there are times when the moon is lined up just right that basically the Earth gets in the way of the sun getting to it? The lunar eclipses occur when the moon goes into the Earth's shadow. Okay, so that's a lunar eclipse. And it only happens at potentially when the moon is in its full phase. So if I go over here, the solar eclipse is when the sun is blocked out, and doing the blocking is the moon. So at its new phase, it's possible that the moon is just right in the right sweet spot for some people on Earth, that basically the entire disk of the sun is blocked out. Okay, so solar eclipses will happen in the new phase. Just possibly. So lunar eclipses can only happen during a full moon, and solar eclipses can only happen during a new moon. And the reason that we don't get an eclipse of the moon every full moon and an eclipse of the sun every new moon has to do with this slide right here. As the moon orbits the Earth, it has a plane, just kind of like the Earth orbiting the sun has a plane. We call that the ecliptic, right? When the Earth orbits the sun, that's the ecliptic. This moon orbit is about 5 degrees tilted outside. So it has to be just right. It's kind of like bobbing up and down. So that's why. So this is trying to kind of highlight there are two parts of a shadow. Like, forget the whole eclipse, but when the sun shines on the Earth, over here on the other side of the Earth is casting into outer space a pair of shadows. Like the really deep shadow called the umbra and kind of the light shadow called the penumbra. Okay, all the time. So that's the umbra and that's the penumbra. So there are 3 types of lunar eclipses, and they are actually listed in order of being really exciting eclipses or being very boring eclipses. So there's 3 of them. The first one is very exciting. It's called a total eclipse, and that is actually when the moon passes into the Earth's umbra. Remember that umbra is that really dark part of the shadow. So the moon passes into the bullseye, really dark shadow, and then passes back out again. So here, September 27th, what we'll see basically is you'll see a normal moon, and then you'll see a bite taken out of it, as a kind of a circular bite, because the umbral part of the Earth's shadow is circular. And then it will be totally in the Earth's umbra, and then it will pass out, okay, out of the Earth's umbra. So that's pretty cool. That's the best one, total lunar eclipse. And then we have a partial lunar eclipse, where just kind of the way it works out, the moon is only passing through just a little bit of the Earth's umbra. And then we have the totally boring penumbral lunar eclipse. I have tried these before, and I do not recommend them. Okay? What's happening is the moon is passing into the Earth's shadow, but only that vague sort of penumbral part of the Earth's shadow. So these are really hard to kind of catch or appreciate, I suppose. Okay, so types of solar eclipses kind of fall into a few categories. Remember, a solar eclipse can only happen when, if that's the sun, the moon is blocking out light from the Earth getting it, just for a select group. We also have kind of an umbral part of the moon shadow. You can see it right here. Okay. So it's kind of cool. I've seen out there on the internet, you can see like a movie from outer space what a total solar eclipse looks like. So the Earth spins, and basically that dark shadow is kind of seen racing across the Earth's surface. So that's called a total solar eclipse. And then the other type of eclipse I have here is an annular eclipse. And the difference is, remember we said that the distance between the moon and the Earth can vary? We call it perigee when it's closest, apogee when the moon is farthest from the Earth. Well, if the moon's too far, basically the shadow doesn't quite touch the Earth's surface. And so it makes, I'll show you what it looks like, an annular eclipse. So there's a total solar eclipse. And actually what you're looking at, it looks like the corona kind of the energy that we don't usually see around the sun. It's a great time to study the sun during an eclipse. This is a partial solar eclipse where this you could not look at safely with your naked eye. Then this is an annular eclipse, where at totality, we say, you basically, since the distance between the moon and the earth is a little bit farther, pushing apogee, then you see a ring at totality. So here's pictures of the eclipse. This actually, figure right here, is as far as solar eclipses go, my husband and I are already making plans for August 21st, 2017, because we're going to go to St. Louis area and catch the solar eclipse. But these are lunar eclipse. This one actually has significance here. I know it says September 28th, but I really think it's September 27th. We better check. But that's the eclipse that we're trying to catch this year. What other slides do I have in this? Oh, that. Yep. So the last bit of topic, we're going to wait for Monday. And let's go ahead and bump your test to Friday. That might make some people happy, some people sad. I don't know. Okay? So there isn't any chapter assignment due on Monday, but we've covered probably enough of this that you probably could get chapter 2 done. Clear as mud.